questions over the stuff that we did last time we started Newton's method? Was able to enter it in R and enter it on Excel. Any questions on that at all? All right. Well, one of the things I want to do today is try to get. What are you doing? Show me. Are you in full screen? Okay. One of the things I want to do today is look at what happens in kind of the weird cases as far as Newton's method not working correctly. We alluded to it a little bit last time, but I want to talk about at least a little bit about what happens in some weird cases. So, pardon me. Goodness gracious. In particular, let's see if I can get the function added back in here. Okay, so here was our Newton's method that we ran last time. Of course, that's right in the way. Why wouldn't it be? Little timer thing is right in the way. There we go. Try to get so you can actually see what I'm typing and not be right underneath the timer. All right. So let's just see if we have a basic function. Pretty basic, but see what happens when we start putting in different numbers and what might go wrong. So let's say we start with the function x to the 10th minus 2. Pretty straightforward function here. In particular, we already know what the roots are. It's not too hard to solve this one by hand, right? Either 10 plus or minus the 10th root of 2, and then 8 complex roots. There will actually be 10 different roots to this particular function. And the reason I know that is because we got a 10th power. So fundamental theorem of algebra tells us that we have as many roots, including multiplicities, you have as many roots as there are power on your degree of your polynomial if you count all the complex ones. We're not going to do, I'll do a little bit with complex numbers, but not a whole lot. I'll show you something today with some complex stuff. But anyway, it's not too hard to figure out what this root is. Remember, to be able to implement Newton's function, not only do I need a function, I also need to go with derivative, right? So derivative here, though, is pretty easy. Since I am just differentiating x to the 10th. I'll have 10x to the 9th. Don't forget to put in your multiplication sign. Otherwise, it'll yell at you. So now we should be able to call Newton's method with our function and our derivative, and then an initial guess. Let's just, for the time being, start with 1 and see what happens. And that one converts pretty quickly to the root, or one of the roots. Thinking about 5 steps, got to the end, out to 6 decimal places, didn't change. So that was pretty quick. But what happens if we chose 1? What happens if we would have made a worse guess? Maybe if we would have chose, say, 0.1 instead. Yeah. Notice in that case, it started off really, really big, right? So let's think about why that happened. Okay. Well, remember in our Newton's method, I'll write it on this. Well, I know I'm recording, but we'll write it on the chalkboard anyway. Remember in Newton's method, our formula for the next guess is the previous guess, and then minus that quotient of the function of the guess over the derivative of the function of the guess, right? And we've got that quotient sitting there, right? Pardon me. Well, notice that I'm putting 0.1 in for x to start with. In this particular problem, what are you doing to that 0.1? Well, it's in the denominator, so we're taking it to the 9th, right? We're doing the derivative, but you're exactly right. We're putting the 0.1 into the derivative. That's the part that's going into the denominator. 0.1 to the 9th is really, really tiny. So you're dividing by a really, really tiny number and getting a really, really big number, right? And that's what's happening here. So notice that we get bad guesses if we're close to horizontal tangents. And it's not too hard to see that this particular function has a horizontal tangent of 0, at 0, sorry. Right? What's the same function? The function, the derivative, you re-entered the Newton. Oh, what is it? Sorry. No, it's fine. X to the 10th minus 2. Oh, your function is undefined right there. The function of x. That's what's causing the problem. that's what it is. It's easy to do to leave off some little thing. You got a comma in there instead of the decimal point. 0.1, yeah. Yeah, yours would come out to be infinity there. It's gonna because it's trying to divide by 0 the way you typed yours in. You're welcome. All right. So again, notice here that when you've got something close to the horizontal tangent, what it's doing is it's throwing your intercept way off, right? Okay. Pardon me. So if you had something like, well, if we just look at the graph, real quick of the particular function, let's go over to Desmos here, get a graph pretty quickly, rather than do it on. Okay. So here is your curve, and what we're trying to find there is the equation of the tangent line, but notice how flat this is, right? Now your tangent line has a positive slope, but it's very, 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 very small positive slope. So it's throwing your intercept, I don't know, out by somewhere by Rockford at this point, right? Okay. That's what's happening. It's just so small. It's going way that direction. Okay. Now eventually it came back, didn't it? It just took it a while, but eventually it was able to, as long as it was in there, back to our studio here, it was, as long as it was able to deal with the number, it was able to come back, and it eventually got there. It just took a long time to do that, right? So when you're doing Newton's method, good guesses are important. So those are one of the things I believe I mentioned last time, but we didn't program it in. One of the things that if you were doing error checking in your functions, in your methods, one of the things you would check for in Newton's method is see if you have a small derivative. Okay? So it might be the first thing that you actually check for. When whatever comes into the function, you check, take the derivative of that particular value. If it's really super small, then kick it out and say it's just too small a derivative instead of trying to calculate. I mean, this one actually got there eventually, but you might have some tolerance level that would say the derivative is too small. In particular, if you had a derivative equal to 0, then your tangent line will never cross the axis, and you don't want to use that at all. So if you're doing some error checking thing, you might want to go along with those lines. Let's do another example. let's look at, I'm going to look at the graph first. Let's just look at the function cosine of x minus 0.8. Zoom in a little bit here. Pardon me. So, let me scooch this over just a little bit. So say you were looking at this particular function and you wanted to find this root that I just clicked on. That one there. Well, again, if I try to pick a guess close to it, it'll probably work pretty well. But let's say let's just play with it a little bit and see where you might get a bad guess here. So let me change my function, f is a function of x of cosine of x minus 0.8. The derivative of that, of course, is negative sine of x. Right? So maybe I took my derivative correctly. There's a reason why I'm not dealing with difficult functions. Okay. All right. Pardon me. So let's plug this into Newton's method. Let's just start with a guess of 6 and see what happens. 6 is pretty close, right? We said it was about 5.64 looking at the graph. So let's do Newton's method of f and the derivative of f in 6. And it converged to what we thought it was, 5.6. Okay. But what if we move over to just a little bit farther over? Oh, up. And maybe go 6.2. Something weird happened there, right? Look where it jumped to. It found a root here. Or sorry, it went to found the intercept for your tangent line here. That was way off to the side. Let's see, 3.8. So that's over here. 3.8 is about here. Then it found another tangent line and it shot it all the way over to 31. And so what's it doing at that point? It shoots all the way over to here, right? And then what happened? It got a little bit better. It went to 27, which is here. And then eventually it honed in on that root, didn't it? 24 point something. Okay. So notice that we said we wanted to look for the one that was close to 6. I found a different one. And again, what's going on with the guess? If we go back to what the graph looks like again, notice again 6.2 is close to that horizontal tangent, right? As a matter of fact, that function has a horizontal tangent at 2 pi. Sine of 2 pi is 0, right? So I pick something close to 2 pi, and I'm getting, again, it's shifting things way off, right? And basically, if you're near that horizontal tangent, and you've got something that crosses multiple times, you could probably pick your guess so that you would get to whatever root you wanted to, just from that one guess. Just by playing around near that guess. Because of the fact that as you tilt that line, when it's a very, very small slope, it doesn't take much of a tilt to make the x-intercept really change. So again, the whole point of this is that you've got to be careful when you've got functions that are pretty flat. Now, the ones that we've looked at so far, have had horizontal tangents, but you may get things that don't even have necessarily horizontal tangents. Pardon me. Let's look at another one here. I'm going to, type in a function here. This one's going to be a little bit more complicated. 2 divided by 1 plus e to the negative 5x, then minus a half. And like I said, a little bit more complicated. But notice in this case, I don't get any horizontal tangents, but I do get a function that's going to end up being really, really flat, right? Right, there's flat on the ends because there's those horizontal asymptotes there. This is an example of something referred to as a logistic function. This is a really good function to model population growth with limited resources. I know you've probably done population growth where you've had exponential growth, just doing a times e to the bx kind of idea. That assumes you've got unlimited resources, but eventually you're going to get some sort of a what's referred to as a carrying capacity. There's only so much that the environment around can handle. And so it'll grow like exponential growth to start with, but then there'll be a point where it just can't get any higher, so it levels off. So again, this is a good model for what we refer to as logistic growth. And again, it's something with limited resources. Business applications talk about law of diminishing returns. That's the same kind of idea, right? You're putting in more and more capital for less and less gain. Pops up there too. Okay. In any event, if we notice that for this particular one, we only have one spot where it crosses the x-axis, right? If we pick something here where we've got a nice slope, we're going to cross pretty quickly and it'll hone in there, right? But if we get past a certain point, it's going to shoot way out, and then we're going to get even flatter, and so it'll shoot way out again, and it'll be even flatter, and it'll just keep going farther and farther away, it'll never even converge. So there's going to be some point here that we get past, but it's just going to be too flat to help it out. So to visualize that, let's say we did, see if I can type this one in real quick. So our function there is, what did I have? 2 divided by 1 plus exponential of -5 times x, and then minus a half. The derivative here, I'm not going to bother simplifying it. What do I get? Write this off to the side here. So I have basically 1 plus e to the -5x to the -1 is what I need to take the derivative of. So I'd have a -1, 1 plus e to the -5x to the -2, and then times a -5e to the -5x. Chain rule, right? And then I've got the extra 2 that would be there because there was a 2 on top, right? So if I type this in, we should get 10 times 1 plus e to the -5x to the -2, and then times another e to the -5x. That'll be our derivative. Pardon me. Notice this. Yeah.
Would you need the -5 times x?
Oh no, you're
Sure. The first one, like 10 times 1 plus.
I put the 2 and the 5 together to get the 10. Is that what you're asking me?
I don't know.
So I just took the derivative of the 1 plus e to the 5x to the -1, but there was also a 2 on top, right? So then we had an extra 2 times that. When I do the 2 times the -1 times the -5, I get the 10. So I just try to simplify it a little bit so I don't have to mix up.
I'm not that feeling like the 1 plus the HB shouldn't be like should have a caret.
Oh, remember EXP assumes that what's inside here is a exponent.
Oh,
Yeah, that is whatever's in the EXP function is the exponent.
So
you don't have to use a caret with EXP.
could we though? Like,
It'll give you an error because it knows that EXP is a function. So yeah, you don't want to put a caret in there. One thing I do want to mention at this point, and it's going to lead us into the next section that we're going to do, the next method we're going to do. Notice that to be able to use Newton's method, not only do I need to know the function, but I also need to know its derivative, right? Okay. So there's a little bit of a disadvantage of that in the fact that I actually have to compute the derivative, which could be nasty. This one's not necessarily all that nasty, but I still have to compute it to be able to plug it into a function. The next method we're going to do, we're not going to use the derivative. Okay. It'll be another one of the iterative methods like Newton's is, where you're going to use previous guesses to generate new ones. Okay. So we refer to those again as open methods, right? With the bracketing methods where we're trying to bound where the root was, versus open methods are you're using previous guesses to get new ones. Okay? So the other technique is going to be the same idea, but we're not going to actually calculate the derivative. What we'll use is something that's going to hopefully help us estimate the derivative, which will lead us into a discussion later on about how do you estimate derivatives. So that's kind of where we're going with all of this. All right, anyway, function, not derivative. So again, if we run Newton's method here, actually I don't, just go back up here. Let's say we start with a root of 0, or a guess of 0, converged really fast, right? Start with a root of 0.5, not so fast. Okay. Matter of fact, what happened? Exactly what happened. I told you was going to happen, right? Okay. Notice that we started with a guess of 0.5, the next guess went farther away, and now we're landed into the land of close to horizontal asymptote, right? Then it shot it over to 60, then it shot it over to somewhere negative 4 times 10 to the 129th, and then it's just like, yeah, I can't do it anymore, it's too big. All right. Yeah. Hit the stop sign. So just wait, what did you type in? Okay, so let's go back to this one here. I guess there's something that's not quite typed right. Function C. Yeah. You guys don't really want to minus 2 there. You guys the function was a minus. Oh, it was minus a half. Oh, you got minus a half. Never mind, it's on there. Sorry. My bad. I lied. I was reading it actually. Oh, that should be EXP. That's what it is. Yep. Oh, I said my guess is you had something an issue with your function. Yeah.
Says there's an error with my function.
That's because yours also says it's going to get too big. Let's see what you've got here. You need parentheses around the denominator. The 1 plus e to the 5 negative 5x for your function. You don't have to retype your function in. Okay. You can just copy that line and paste it down and then put parentheses around it. That's what's causing it.
I was just saying 2 over 1.
Yep, exactly. Okay. Yep, that's what it's doing.
I knew I did something wrong. So.
Yeah, no, it happens.
Did it just stop because it hit like the tolerance level?
It stopped because it's getting a value out that is beyond the capacity of the computer to hold. So it's just too big. So it can't actually compute. Would have been the new guess is too big at that point. And once the new guess is, this is giving an infinite answer and it doesn't know how to do this. So it's trying to compare the absolute value to the tolerance, but it's giving something that's not a number. And so it doesn't know how to interpret that syntax. And so that's why it's getting us in here. Okay. All right. So again, moral of the story, initial guesses are important. Okay. So you don't want to be, basically, flat spots are bad, right? You can also get some weirdness, and they give an example in the, well, they give you a picture example in the book. You can actually get some, also other weirdness, pardon me, where your roots will just cycle back and forth. You'll just hit the same 2 every single time because it's just the way that it's basically kind of a symmetric nature of the function. You'll get a tangent line that goes one way, and you can hit the x-axis, you put it in, and it goes back to the exact same spot where you were. They'll just cycle back and forth. So another thing that you might want to consider as you're if you're actually doing these kind of things in practice, like I said, right now, I'm only worried about trying to get things programmed up and make sure we understand how the algorithms are working. Okay? If you were actually doing this, honest to goodness, in practice, you would need outs. You don't want things to hang up, right? So you might count how many times you've gone through. And then if you hit a certain number of iterations that you're just like, I need to quit, you'll quit. Okay? So that'll give it an out. Checking if you've got a small derivative before you even try to apply it. Right? That'd be another way to give it an out. Okay? There's lots of different things that you might want to test as you're going along to make sure that you're not going to get these errors. Again, that is a practical matter for when you're actually out in the workplace trying to implement these types of algorithms. And these algorithms are important. They are actually used out in industry, and more complicated ones, of course, as well. But think about why you might want to have zeros. One of the things that you do in derivatives, in calculus, you set the derivative equal to 0 because you're looking for critical numbers because you're trying to optimize things, right? Optimization is exceptionally important in business in general, right? Trying to minimize your cost, trying to maximize your revenue, right? Try to minimize time it takes to do something, right? There's all sorts of optimization types of things that you need to do out in business. Root finding methods are important to be able to do those kinds of things. So, anyway, I'm only worried about us getting these things implemented. I'm not worried about the error checking. If we were doing honest to goodness, hardcore computer programming kind of things, then we wouldn't concentrate on those things. And that would be something that you would need to worry about out in the real world.
What if something has multiple roots? Does it matter which one we like take a guess to?
If you've got something that crosses the x-axis multiple times, then you'll need to make sure you pick guesses that are close to where those roots are.
You feel like for any reason now, like would it matter which one we're trying to estimate?
It depends if you're asked to find all of them or a certain one or what have you. Now, if you have when you said multiple root, it did make me think of something else. When you have a root that has a multiplicity greater than 1, where it's tangent to the x-axis, this method will fail. You're gonna have issues because again, you're getting those horizontal tangents again. It's gonna cause issues. So, yeah, anything that's gonna be real. If you've got zeros that are really, really, where the slope's really, really small, so you get to Newton's method. Good news is that this is why we talk about more than one type of method. Bisection method won't fail. It's usually longer to converge than Newton's method. But I mean, people study optimization procedures. I mean, people do research on this to try to get things to go faster and faster. Questions on that at all? One of the things I do want to talk about, we've already mentioned this from a visual standpoint. One of the things that we wanted to talk about was, pardon me, how good the convergence is. So we know that every time you use the bisection method, you get a half of the interval each time, right? So you have a sequence that you can follow that tells you how quickly it should converge. Pardon me. For Newton's method, I use the computer, that's right. For Newton's method, let's look at what we have. So, anyway, when you're doing Newton's method, we know that we're using a linear approximation for the function, right? That's the whole idea, right? So when you're doing Newton's method, we're approximating the function, again, using that tangent line idea. We know that our y is approximately the next one in the sequence of the y, that f of x, the y is approximately f of x of n plus f prime of x of n times x minus x of n, right? We agree with that? That's the linear approximation that we're trying to use to figure this out, correct? Yeah. Now, we know that this crosses the x-axis. We've already done this. This is how we got Newton's method to start with. We know that this crosses the x-axis, and we set it equal to 0. That's how we figure out where it crosses the x-axis. Now, one of the things that you learn, either in Calc 2 or Calc 3, depending on when you've talked about Taylor series, is that we're going to talk a little bit more about Taylor series here next week. When you have Taylor series, we know that we can write our function centered at a particular point as f of x sub n plus f prime of x sub n times x minus x sub n, and then second derivative over 2 factorial times x minus x sub n squared, and you continue, right? You keep taking more derivatives and dividing by the higher and higher factorials to get those coefficients. That's our Taylor series expansion. Notice that if I lop off the end, that's our tangent line approximation, right? We refer to that as a Taylor polynomial of degree 1. That's our linear approximation. If we want to do another one, that would be a Taylor polynomial of degree 2, quadratic approximation, and so on down the line, right? Now, you don't prove it in Calc 2 or Calc 3, depending on when you learn it, but Taylor's theorem says that if I want the exact value of the function in somewhere where it converges, then I can replace, at some point, I can always replace that end piece with the value that we have somewhere between your x that you're looking at and the x of n, or the center, I should say. You can always replace this with a single term. Kind of looks like a mean value theorem idea, right? Remember your mean value theorem said that somewhere in the middle, the instantaneous rate of change has to equal the average rate of change. Taylor's theorem is kind of that idea on steroids. Somewhere in between the 2 points, there is a point at which this entire piece that you lop off can be written in terms of something that looks like this, just the first term that you lop off, the leave off, I should say. Okay? So if the x sub n, if this x sub n is the root, then using Taylor's theorem, we can write 0 equals f of x sub n plus f prime of x sub n, x minus x sub n, and then plus, we're going to write it as f double prime of, well, I have a guy I've done some research before calls that tornado. I don't know how to, xi, xe, whatever you want to pronounce it in Greek. Okay? Told you mathematicians like their Greek letters. Okay? So I can replace this entire piece that we drop off with something that looks like the first term that we drop off, where this value that we picked is in between whatever you're trying to plug. Oh, I should say x. I wrote the wrong thing. I got to fix it here in a second. Oops. Undo. I said if we've got a root, then we have this equal to 0, but I forgot to actually plug in the root. Let's say that x sub r is your root here. I just need to put a subscript of an r in there. X of r is the root that we're trying to approximate. If I plug it into the function, I better get 0 out. Taylor's theorem says that I can use the linear approximation, and then I have a term over here that's dependent on the second degree. It's dependent on the term that we left off, the first term that we left off. Okay. All right. So what do we mean by error here? Well, error in the next term, the error in the approximation for the next root is going to be just the difference between your guess and what the actual root is, right? We agree with that? So the error, if I use a capital E to denote the error, it doesn't matter what the, I'll use an I. It doesn't matter what the subscript is. The ith error, when you're trying to use the approximation, is literally just this difference, not n, x of r minus x of I plus 1, right? Doesn't matter what the I is. I can compute the error just by subtracting, right? That's how far apart they are. We agree with that? Okay. All right. So if we want to get an approximation, or sorry, we're trying to figure out what a bound is on this error. So if this is my I plus first error, we should also be able to play with this with the ith error here. So let's look at the different pieces. So, oops, what did I just do? Oh, there it goes. Let's look at the different pieces that we have here. This was our Taylor approximation, right? We also know that when we do our linear approximation for our root, how we get the next x of n, we set the linear approximation equal to 0, correct? Right? Yeah. So if I take, right now we've got this equation equal to 0. If I take the intercept for this one, the intercept for that one means that you're going to plug in x of n plus 1, right? Because that's how we get the intercept, is we put x of n plus 1 into the line, right? That's how we find the intercept. We would have 0 equals f of x of n plus f prime of x of n times x of n plus 1, oops, minus x of n. That's just how we got the next approximation, right? Because x of n plus 1 represents the x-intercept of the line, the tangent line, right? Now let's subtract the second equation from the first, right? Let's subtract the second equation from the first. Notice your f of x of n's go away. Yeah. Here I can factor out an f prime of x of n. When I do, my x of n's will go away, right? So when we subtract, we get f prime of x of n times x of r minus x of n. Sorry, I forgot my 0 in front. Got a 0 equals. And then we get a plus f double prime of this x of, or this xc idea, tornado, 2 factorial, and then x r minus xn quantity squared. Plus 1 on there. Sorry, forgot my subscript. I know, lots of symbols. Now, I'm not going to make you redo all of this anytime. I'm trying to get to where the error is and why it runs just faster. Okay, that's the whole reason why I'm doing this. Okay, all right. What's another name for this difference here? In terms of what I wrote right above it. What's another name for this difference? The error in the n plus first guess, right? What's another name for this error, or this difference? Error using the nth term, right? So let's solve for the error in the n plus first in terms of the error for the n. Okay? Well, notice that I've got this x sub, the xe guy here, right? Now that xe guy is close to xn, and it's also close to xr, correct? And the idea is that if we're also converging, the x of n plus 1 should also be close to x of r. In particular, both of these, the xe and the x of n, should be close to x of r, right? So if I solve for the n plus first error and approximate these values with x of r, we should get the following. You should get to the n plus first error is approximately the negative of the second derivative at the root over 2 times the first derivative at the root times the error from the nth term squared, roughly speaking. Now, I waved my hands a little bit at this, obviously. Okay. But let's look at this. Notice that we've written it in terms of the second derivative and the first derivative at the root. Does the root change? No. Okay. So this is just some constant. For the whole problem, this is just some constant, right? If your errors, this should be e sub n, it looks like an r, that's an n. This, if your error, if you start close enough to your root, this should already be small. When you square it, it gets even smaller, right? And then each time, your error is going to get small in a quadratic way, because the error is getting squared every single time. So it's going to get smaller faster. We refer to that as quadratic convergence, the name for it. Okay? Because I can write the error in the next term in terms of the square of the error in the previous term. Now again, we have to have nice things happen. I don't want my root to have a derivative of 0. That would be bad, right? And then we also did some hand-wavy things of saying that we were already close. Notice that if our error is bigger than 1 and we start squaring, the error gets even bigger, right? So we need to make sure that we're close to start with. But if we're close to start with, we get fast convergence. And we saw that last time when we compared bisection method to Newton's method, right? Okay. So that's the idea here. It's the only reason why I wanted to go through it. This is why it gets faster. Okay? This is why it converges faster. When it converges faster because of the fact that you square the small error each time. So that you get your error cut down by smaller and smaller pieces. Versus bisection method, your error is bounded by getting cut by a half each time, right? Literally the same constant each time because you cut the interval in half, right? So worst case scenario, your error is going down by a half as much each time versus this multiple of some square of an error, which is going to be much smaller. All right, any questions on that one at all? Before I talk about the next method, I do want to show you one of the homework problems I asked you to do. Talks about using Newton's method with complex numbers. Good news is you don't have to change anything with complex your Newton's method. The way the Newton's method is written will work. The only thing you have to do is know how to enter a complex number into whatever this is called, R. Lost my train of thought there. The only thing that you have to do is know how to enter a complex number into R. Remember that your standard form for a complex number looks like that. And that's literally how you're going to type it into R. There's I'll say 3 quirks. Okay. Number 1 quirk is, remember every other time we have multiplication, we put an asterisk there? We don't put an asterisk there when we want it to be complex. Okay. Quirk number 2 is if I have, say, 2 plus I have to put the 1 next to the I. It literally needs that number. And then third is if you have either of these as 0, you have to put the 0 in. Okay. So there's 3 little quirks. One is you do not put the multiplication symbol next to the I. Okay. 2, if you have a coefficient of 1 on the I, the coefficient of 1 has to be there. And 3, if either the A or the B is 0, you have to put the 0 in there so it understands that you're talking about a complex number. Okay. I know it's quirky, but it'll work. And it'll do any of them. So for example, if I put in 0 plus 1I and tell it to square it, well, I squared is equal to what? Yeah, so now it puts out -1 plus 0I. So it knows how to deal with it. But this is literally what you do. If you want to have Newton's method already programmed in there, you can start with an initial complex guess, and it will converge to a complex number if it converges correctly. The homework problem that I gave you just have to make sure that you plug in the value correctly. That's the only thing I needed to mention about complex. Yes.
This is just a question about R itself.
Mm-hmm.
Is there a way to easily convert a complex number back to a regular integer? I don't actually know.
If it looks like this and convert it back to real, I'm sure there's a function in there that does it. I just don't know what it is off the top of my head. Yeah, I'm certain there is a way. If it is you can, you should be able to pull off the real part and the imaginary part. So you can say if the imaginary part's 0, then just make this set a number equal to the real part. And it should do that without any issues. I don't know what the function is off the top of my head, but I'm certain it does it. All right. In any event, that is what we did for Newton's method. Now, we've already mentioned that one of the disadvantages of Newton's method is that you have to type in the derivative too, right? No matter if I'm doing it in Excel, no matter if I'm doing it in R, however you want to do it, you have to have the derivative in order to be able to use Newton's method. You don't have a choice, right? It would be nice to have a root finding method that only involves the function, right? Now we had one of those when we did bisection method, but again, the problem with the bisection method is that the convergence is fixed on how it converges because you're cutting the interval in half each time. So we want something that has hopefully the advantage of Newton's method, where it's faster, but not require taking the derivative. Okay. And so what the method we're going to use in this case is what's referred to as the secant method. So this is section 3.3. And basically, this uses what you did in Calc 1 when you started figuring out approximating derivatives, right? Before you learned derivative rules, you did approximating derivatives using secant lines, right? And that's exactly what we're going to do here. Assuming that you've got 2 points that are close together, under normal circumstances, if there's not weirdness going on, your secant line should be fairly close to your tangent line. So we'll use that instead. Okay? So the idea behind that is if we have, just to draw a quick picture here, if I have a function and I'm trying to estimate this root, well, I might choose not 1, but 2 points to start with. And connect the dots, like so. Kind of like so. Didn't draw the best picture, but that's the idea. That only involves calculating the function at initially 2 values, but when we iterate now, we'll only have to add in 1 new value. Okay? So notice that we don't have to calculate the derivative at all. Right? And again, if your guesses are relatively close together, then your slope of your secant line should be close to your slope of your tangent line. It should be close to the same approximation. And in fact, the formula we're going to use is going to look very, very similar to what we have for Newton's method. Now, how do you make your new guess? Well, it's the same idea. This tangent line crosses the x-axis somewhere, right? So let's say, for argument's sake, let's say this is your x1. Let's say this is your x2. This is your starting ones. This would be now your x3. And instead of using now x1 and x2, we'll take x3, plug it into the function, and calculate your line from x2 to x3. Do it again. This will be your x4. And then go plug that into the function, go from x3 to x4, and just keep doing that each time. So when we calculate x3, we technically are replacing x1 with x3. When we go to x4, we'll replace x2 with x4, and so on up the line. Okay. Again, notice we don't have to calculate the derivatives now. All we need is a function and 2 points to start with, but only after that first time do we have to do one computation. We only have to plug in the point into one place, right? So that's also, not only does it save you the time to from having to calculate your derivative or having to calculate an approximation for the derivative. Like I said, we'll talk about that in chapter 4, about how we can get derivative approximations. Not only does it save you the derivative calculation, it also cuts your calculations in half of plugging things in. When we did Newton's method, we always had to plug in the point into the function and the derivative. We had to do two calculations. After the first step, we only have to do one new calculation each time. So it cuts your number of calculations you have to do in half. Again, when you're looking at solving problems on a large scale, speed is important, right? So anytime that you can cut down on computations, that's a good thing. Okay. All right. So anyway, this is the whole idea for the method. So if we just talk about how we would do this, if I've got the point, I'll call it x of n minus 1, f of x of n minus 1. And the other point, x of n, f of x of n. We can calculate the line through those 2 points, right? The slope would be f of x of n minus f of x of n minus 1 over x of n minus x of n minus 1. And if we use the point x of n, f of x of n as our quote-unquote base point for our point slope form, I'll have an f of x of n subtracted from the y and an x of n subtracted from the x. Notice this looks almost identical to our tangent line formula. We've just replaced the slope of the tangent line with the slope of the secant line, right? Just took out f prime of x of n and put in this calculation for just slope of a line. One of the things I think is coolest about this stuff is that we're just using high school algebra stuff that you learned, right? Right? You learned how to do equations and lines back in Algebra 1, right? That's all we're using. It's kind of fun, right? Now do the same thing that we did. What we're interested in is we're using this line to approximate the function, so we're trying to use this line to approximate where the function crosses the x-axis. So just like we did for Newton's method, we'll put 0 in for y and solve for x. That'll be our next guess, right? But notice that it's going to look almost exactly the same because remember we divided by the slope. We'll divide by this thing. To make things look a bit nicer, we'll multiply by the reciprocal, right? Okay. So if we go through all of this and finding the y-intercept here, you'll get that your next guess, x of n plus 1, is equal to your previous guess minus the reciprocal of that slope. times f of x sub n. Pardon me. Remember, for Newton's method, it was f of x over f prime of x, right? You can think of that as 1 over f prime of x times f of x, which is exactly what that is now. It's just 1 over the slope, right? We just reciprocated it. Just looks a little bit nicer if we write it this way rather than writing a quotient in the denominator. Okay. So notice this is a this looks almost exactly like what we had for Newton's method. Again, when we change up for Newton's method, we'll just need to make sure we take in one function and two initial pieces, right? We need the two pieces to calculate the slope, right? So let's go up here, see if we can make a function. Oops. I need to pass in a function, and I'm just going to call it a and b just for simplicity's sake. You can call them whatever you want. I don't care what you use for notation there. And then, of course, just like everything else, we'll put in a default tolerance so that we have a way to kick out our loop. I'm going to compare Newton's function that we have typed up right here with this one. Notice that when we did Newton's method to start with, the first thing we did was calculate the new guess so that we had things to compare in our while loop, right? Let's do the exact same thing here. Again, just to simplify the letters, I'm going to call it C. This, oops, I don't have it up on the screen. Is not what I want to do. There we go. There is our formula, right? So the A is the x of n minus 1, and the B is the x of n, right? Okay. I'm just doing it in that order. A is the second previous, and B is the previous, okay? So when we type in our guess here for C, our C will be what? It'll be B minus parentheses B minus A divided by f of B minus f of A times f of B. Yeah, I'm just using single letters here because I was lazy. I didn't want to type a bunch of things. Okay. But again, I want to calculate my new guess against my old one. Remember, the C is going to replace the A, right? So when I do my while loop, I want to compare my B and my C together, right? Okay. So my condition here will be while the absolute value of C minus B is greater than the tolerance. And notice again, looking at, just comparing it again with Newton's method, it's exactly what we had typed here, right? The C, I could have done B minus C, I'm doing absolute value, so the order doesn't matter. But the B is my old guess, my C, the nearest previous old guess, I should say, and the C is the new guess, right? The A is the thing being replaced. That's why I'm comparing the C with the B. Does that make sense? Okay. Now, just so that we can see the numbers here, let's print the C just so that we can see the value that we're getting. Again, I want to compare a number of times through, so I'm just going to put that in there so that we can see how many steps it takes to converge. I want to replace the A with the C, essentially, right? But I want to make sure that I'm doing it each time. So it's probably easier to make the A the B, and the B the C, and then calculate a new C, right? Just basically shift everything. So we'll take the A to be the B, to be the B, and the B to be the C. And that'll shift everything, right? That gets rid of the A and moves the B as the two previous, and the C is the next the previous now. And then calculate the C again. I'm just going to copy this down. Okay. Again, I want to compare this to Newton's method, how we typed it in. We only had one guess each time in Newton's method, right? So I just replaced the guess with the new guess and calculated the new one again. This one I have two that I always have to work off of because I'm using 2 points to generate the line. So I'm moving A off, shifting B over essentially, right? And then making B the new one, and then calculating another one. Does that make sense how we're doing that? Okay. Just kind of making a assembly line almost. The A falls off, the C comes on, then the B would fall off, and the next one would come on and keep going. Finally, once everything kicks out, I'll return whatever the C value is at the end. The last computed C that we did, we'll just return that once it gets our tolerance. We okay with that? All right, so let's see if this will run. Need to bump this up. Oh, hey, not that far. So scroll that up a little bit, maybe. Okay, boop. There we go. Let's run that. Okay, didn't get any errors there. I apologize for the silly thing in the way, the timer in the way. All right, let's just go back to the original function that we did, the first example that we did way back. Oops, I do have an equal sign there. One of the first examples we did that e to the x plus x, because we knew that the root was around negative 0.57-ish, right? Somewhere around there. When we've done the calculations before on this, bisection method took in the mid-teens number of steps to get it to converge where we wanted it to. Newton's method took 4 or 5, right? Somewhere in that vicinity. Let's see what secant method does here. And again, the reason why I'm doing the same examples, I'm just trying to compare the methods, right? To see how quickly they converge. All right, so secant of f. Now again, we have to put in 2 initial guesses here, right? So I'll just do 0 and -1 and 0, because we know it crossed somewhere between -1 and 0. Good news is that you really don't, with the secant method, as long as you're close to the root, you don't have to bracket the root. Okay? I could have used 0 and 1. They were both on the same side, but you're still just using the line to figure out the next one. Okay? So you don't have to worry about bracketing it like you do with bisection method. Okay? Also, the way we wrote our function to do the secant method, it doesn't matter which one's the bigger and which one's the smaller. Right? We're just going through and cycling through. All right. Notice in this case, it took about 5. Newton's method's still in here, I believe. Newton f. Oh, I gotta compute what the derivative is first, just to compare the two and see how many steps they were. That was exp of x plus 1. And now let's do Newton. Oh, I forgot to say type f, derivative of f, and 0. Secant method took 5 steps. Newton's method took 4. Relatively the same, right?
Is this just because you had a better guess for Newton?
No, actually, it turns out Newton's just always a little bit better. And I'll talk about what that is just briefly. I'll go through all the details that we did with the error for Newton's method. Newton's method's always slightly better as far as convergence goes. The process of getting this in, okay. Again, advantages to secant method are you don't have to worry about taking your derivative. That's a big advantage, right? Now, what we lose is just a little bit of convergence speed. It's not too bad as long as everything is working well, right? We could, of course, run into the same issues like we do with Newton's method. In particular, if you hit two outputs that are equal or close to equal, we're going to get that small derivative or a small denominator again, and it'll throw your x-intercept way off because you have a line that's nearly horizontal, right? So you have the same kind of issues with that. But again, the advantage here is that you don't have to calculate a derivative. You get a function in there, a couple initial guesses, and you can go. Okay? But you have to be a little bit careful when these are close together. If these are close together from calculus ideas, if these are close together, these also better be close together in order to get things to cancel out nicely, right? That 0 over 0 idea. Okay. If you got these two things are close together and those aren't, you're going to be in trouble. So you could have a similar type of issue there. All right, so remember when we talked about the error in Newton's method, we got the exponent to be a square, right? The next error in the sequence is roughly some constant times the square of the previous error. In the secant method, and you can go through what they do in the book. Well, they kind of do it in the book. I'll tell you what I mean by kind of in a second. We're in section 3.3. It starts on page. This is why I'm not going over it. It's this discussion of the error starts on page 144 and ends on page 147. Okay, I mean it actually is kind of cool. The Fibonacci sequence pops up in it. That's kind of weird in the error analysis. The Fibonacci sequence pops up in all sorts of weird places. Fibonacci sequence pops up in the error analysis, and it turns out you don't get quite quadratic convergence, but the exponent you do get to replace with the golden ratio, which is fun. So you get 1 plus root 5 over 2 in the exponent. So it's about 1.6-ish. Okay, it's not quadratic, but it's better than linear. Okay, so it goes faster than the bisection method. It's almost as good as Newton's method. Like I said, it's interesting in the fact that Fibonacci makes an appearance and golden ratio makes an appearance. That's kind of cool, right? Wouldn't expect Fibonacci to come up in an error analysis for solving an equation. The reason why I'm not going through it in class, I just told you it's 3 pages in your book, 3 to 4 pages in your book, and that's not the whole proof. It actually says at the end, this inequality can be shown and proved in general, but it's long. I'm like, you just took 3 damn pages to do that. Okay? So that's why we're not going over it. But I didn't want to mention it because it is a cool thing. Fibonacci pops out of it. Fibonacci makes an appearance, which is really, really cool stuff. Any question on the method at all? All right. So we've learned 3 different methods for solving these equations. We learned the bisection method, which is when you have one of those bracketing things. The reason why we call it bracketing is because we have guaranteed that we put the root in between 2 things. That's what the bracketing method means. But with what the convergence there, we know only converges a half of the length of the interval each time, right? We're fixed on how quickly it can converge. Versus we did Newton's method first. It's an open method. Open means that we don't necessarily have the root trapped in between anything. That's what open means. We're just using guesses and iterating to it. Okay? Newton's method involved looking at linear approximations, stuff that you did back in Calc 1, and estimating where the roots are. Right? Then we did secant method today. Same idea, open method, because all we're doing is iterating through to get new guesses. We're not bracketing the root anywhere. Okay. In fact, like I just mentioned, the two guesses might be on the same side of the root. The function might be positive in both of them. The function might be negative in both of them. Okay? It doesn't have to be on either side of the root. I picked -1 and 0 here just to plug it in, only because I was trying to compare it to like what we did for bisection method and Newton's method, something close. Right? That's why I used those numbers. But I could have used something different. If he would have done, say, secant of f 0 and 1, I still get there. It just takes a little bit longer. Right? But 0 and 1 would have been on the same side of the root. Because we can still get down to that negative 5.7, 0.57-ish. So those are the three main equation solving techniques that we have with the computer. Okay. You should be able to, like we did with Newton's method, you should be able to put this in Excel. That'd be a good practice to try and see if you can get the formulas put in Excel correctly. Okay. You can always ask me about it too, but see if you can get the formulas put in Excel correctly like we did with Newton's method. We'll talk about, we're going to switch gears slightly next time. We're going to talk a little bit about storage in the computer with numbers and how the computer stores things. Talk a little bit about that. We'll also talk about doing other computational things a little bit more quickly. We've already mentioned that we want to do things a little bit more quickly when you're doing large-scale computational problems. So we'll talk a little bit about how we can do polynomial evaluation a little bit more quickly. Taylor series, again, good way to approximate functions using a polynomial. But calculating those coefficients can be not very quick, right? Because you have to calculate a whole bunch of derivatives and look for patterns and get all those things. We're going to talk about a quicker way to do that too. Okay? Of course, all numerically, so that's the whole class. Okay? All right, so we'll do that next time. As far as your homework goes, you've got a couple of options for turning it in. You can either write out, like if I ask you to use Newton's method on something, you can just write out what the numbers are that R is giving you. Write out the command, write out the numbers. You could also take a screenshot, put it on the document, send it to me. You could save an R file, do it that way. Or if you're using Excel, you can save an Excel file and send that to you. Any of those methods work. The one thing that I do want you to make sure that you do, not necessarily concentrate on, but make sure that you're able to do is like the first problem where I wrote by hand do the first 3 steps. So that tells me that you understand how the algorithm is working, and that would be what would be like on one of your quizzes in class. Okay. Does that make sense? Okay. All right. So homework that you do on Tuesday. Of course, come in with questions either in my office, ask questions in class on Thursday, either or. We're going to jump back to chapter 1 for a little bit and talk about again how the machine stores numbers, and then some other quicker ways to do some calculations. There's lots of stuff in chapter 1. We're going to distill it down to just a couple of things. Okay. All right. Have a good one, everybody. We'll see you on Thursday. Yes.
And we should be working it out.
You walk the work together over?
And we should be working it out. Okay.
Yeah. I don't care if you talk to each other.
All right.
Yeah. See ya. How's the status? Last good one? Good?
Yeah.
Oh, good.
Like,
I know it's weird since you're not
but
there.
it's just a bunch of
Yeah, I
things
know.
down here stopped working, so
Yeah.
I just made one.
I've worked